Well, welcome everyone. Thank you for joining us for today's webinar, Safety or Safety Critical, the Identification and Management of Safety Critical Elements, SCE, and Safety Critical Systems, SCS, presented by James Birch and Wayne Repick. Now, for today's webinar, I want to go over a few housekeeping items. First, we want to respond to your questions following this webinar. Please type any of those questions into the Q&A box in the Zoom control panel, and our presenters will respond to the questions. Finally, at the close of our webinar today, please provide feedback by responding to our survey, where you can provide recommendations for today's presentation and future webinar topics. We are excited to have James Birch and Wayne Repick present today. So without further ado, I'm going to turn the time over to James first.
Brilliant. Thank you, Naomi. And good afternoon, everybody, or good morning, good evening, depending on where you are in the world. Thank you for joining us for this webinar. So, as Naomi said, safety or safety critical, to talk about the role of safety critical elements. And I'll be joined later by Wayne Repick, and also we have a special guest with us today, Amar Hassan, who's an independent part-time consultant with Baker Risk, who'll be joining us towards the end of the presentation when we get to the Q&A session. So without any more ado, let's get started. I'll give you a very short overview of the day, a little bit about Baker Risk for a minute or two. Then I'd like to get into really the role of safety critical elements in major accident hazard events, how we identify them, how we set performance standards, and then quite critically, how we maintain them, how we ensure they're there when we need them, and then some time at the end for questions and answers. So myself, based in the UK, Wayne is based in Texas. My background is 35 years in operations in chemical industry. I joined Baker Risk about a year ago. So why? Well, Baker Risk, we're here to save lives and make the world a better, safer place to do business. We're here to study dangerous phenomena, to learn how to manage them and mitigate their effects. We're not a large company. We're employee-owned entirely, founded in 1984. And we have a very, very high proportion of scientists and engineers with long service histories, both with Baker Risk and in the industry. We have offices across the US, Canada, UK, in Egypt, and shortly in the UAE. We have two significant test facilities which allow us to do outdoor trials on fires and explosions, the materials lab, and several joint industry programs that we manage. And what do? We cover process safety. We have a strong presence in protective structures and structural engineering, which covers blast effects, damage to buildings. We provide accident investigation services. We have a training center. We have testing capability. We have our own software development group. We develop a lot of our own software based on our own trials. And we have an organization within Baker Risk, Fortress Protective Buildings, where we produce prefabricated blast-resistant buildings, which can provide not only blast resistance, but also toxic shelter in place. But our reason for being are the catastrophic events, the serious, the damaging, life-threatening, business-threatening events. And our creed has been that if we can predict and understand them, we investigate them, we test, and we know how to mitigate them. So this is a quick overview of the process safety services we have. Through process safety management, the identification of hazards through hazard, HAZOP, LOPA studies, facility siting studies, and QRAs. Purpose being identify hazards analyze the risks, and manage the reduction. Process safety, we have many people in our organization who we might say have written the book. We've collaborated and produced several books for the CCPS. We run a series of joint industry research programs covering explosions, pressure testing, ammonia and fertilizer studies. And we contribute heavily to a lot of the API standards. We have members on the panels who develop these standards. And we work across a wide range of industries, of services, government, offshore and onshore. We're heavily involved in industry safety organizations and in conferences and working groups. So in the US, in the UK, in Egypt, we maintain a large presence, trying to present and share the learning and knowledge that we have from our work. So with that, I'd like to start on the main topic of the day. Safety critical elements and their role as barriers, as protections against major accident hazards. If I steal a bit of wisdom from Trevor Kletz, who is often called the father of process safety. He famously said, if you think safety is expensive, try having an accident. Accidents cost a lot of money. Sadly, accidents, particularly major accident events, cost a lot of lives. They can destroy lives, they can destroy businesses, they can affect the environment. They are the serious ones we have to study. Now, using that wisdom, we put a lot of effort into preventing these things happening. But it's important that we understand the balance we're dealing with. Not everything on our plants can be safety critical. We would not be able to resource, we would not be able to afford to run many of our processes if we said that everything connected to safety was absolutely critical. The burden would be so high, and there is a risk then that we devalue the system. But the opposite is probably more damaging, because if we don't classify what is safety critical, then we're putting lives, we're putting our businesses, and we're putting the environmental at an unacceptable level of risk. So we have to make those judgments. And that really is the first stage I want to talk about today. So what actually is a safety critical element? The definitions used by EGPC, by IOGP, by Energy Institute, revolves around saying a safety critical element is any part of a facility or a plant or a computer program, and that's an important one to remember, which if it fails could cause or contribute to an MAH event. So that might be a pressure vessel that fails. But also let's consider the other side of this, which is that it's any part of a facility, a plant or a computer program, which is put there to prevent or limit the effect of a major accident hazard. So that might be the fire water system, that might be the sprinklers, it might be bunding and containment. So we try and consider both those parts of the definition. There are also a number of other safety critical concepts which I'm not going to go into in a lot of detail today. We'll cover some of these in a future webinar. But just to understand terms that get used. We talk about safety critical equipment, which is sometimes a little confusing because of course it abbreviates to SCE the same way as a safety critical element. But safety critical equipment is when we're talking about the instrument or equipment tag level. So part of the safety critical element. Safety critical systems is another term you'll hear, which is often used to describe a collection of safety critical elements. But again, sometimes can be used talking about systems involving people, procedures. And that's where it can become interesting, because as we know, we're not perfect. We were not created to be perfect. So all our systems will have weaknesses. So it's important to consider here that we have to allow for human failings, human errors, and the concept of human factors and safety critical tasks comes into play. And again, this is something we'll talk about more in another webinar, but just so that I've given you a picture of all the things that may come up in this area. And then the last one is environmentally critical elements. And this is really the same concept as safety critical elements, but as applied to the environment. So just put some definitions up there, and then we'll go into a little more detail about safety critical elements. The problem we have is that major accident hazards are so serious, we just cannot take the risk of them happening. They can destroy a business, they can kill many people. So we want to give ourselves as much protection as we can against that. And this is often known as multiple layers of protection or defense in depth. So we try and give ourselves many ways to stop the accident happening and many ways to try and mitigate its effects. We don't want to rely on just one thing only. And often this is an easy way to visualize it. We have these layers within our process, layers of protection or barriers. And at the bottom in green, we see the normal band where we hope our plants are going to be running. Steady, safe, process parameters where we want them. But we know occasionally perhaps temperatures or pressures may become too high. And we have alarms and we have trips and interlocks to try and bring the process back into control. If those things don't work, we give ourselves another layer of protection, which is emergency shutdown. And this might be depressurization systems, it might be quenching, reaction kill systems, where we hope to turn the trend, bring us back into a safe condition. But after that, we're into dealing with what is an emergency. And we try and control the level of that, but this may be relief valves, this may be containment against spills. But ultimately, if none of these work, we're dealing with emergency response, which is our emergency systems, our firefighting, life-saving. So if we look at all those layers, which are there to try and protect us as many times as we can, let's just go back to my earlier comment that we're not perfect and the things that we create are not perfect. And a useful model of that came from Professor James Reason about 20 years ago, who proposed this concept of Swiss cheese. And the Swiss cheese in question actually has bubbles of gas inside it. And if you slice the cheese, you get a piece of cheese with holes in. And his concept was that that's what many of our barriers are like. We may not realize those holes are there until we slice the cheese. But if we have a hazardous event hits the barrier where the hole is, it will go straight through. It will not be stopped. So we hope that we have other barriers after that, which are strong at that location. But there is always the chance that those holes line up. And eventually the bullet travels through to the point where we have an incident. So we have to monitor the condition of our barriers. We have to know that they're functioning and they'll be there when we need them. And that's a key part of process safety management. So we tend to have two classifications simplistically for barriers. And that is active and passive. And just to explain, A passive system is one that doesn't need any energy, doesn't need any power to operate. And this would be something like a blast wall or a containment dike or a bund. We put it in place, and as long as it doesn't deteriorate, it will function. It doesn't need electricity, it doesn't need compressed air, it will function. And then we have active systems which are capable of doing more complex things. And these need perhaps electrical power. So for example, fire and gas detection system. Fire water, we need power for the fire water pumps. And these are safety critical elements that provide an action on demand. Either the emergency button is hit or a trip is activated and the action is provided. So of course, these are the ones where we focus on testing them by actually demonstrating what happens. So let's just keep in mind we have these two. We have active and we have passive. Different approaches, different benefits, but the two together make it stronger. So let me just summarize those models and points quickly. Safety critical. We have to make sure we're focusing our resources where we need them, on that which is truly critical to preventing major accident hazards. We try and do that by having layers of protection, many of them, different approaches, so that if one of them fails, another one will save us. The concept of the Swiss cheese tells us that the barriers may not be perfect. We need that chronic unease, that vigilance to keep checking, to keep looking for weaknesses and fixing them. And then finally, the idea of both active and passive barriers. So that hopefully sets some terms I'll be using later on, and really why SCEs are important in dealing with major accident hazards. So what I'd like to go on and talk about now is, how do we identify them? How do we find them? How do we select the right type? How do we make sure that we've got enough and not too many and not too little? So for that, let's consider what happens when we have a fire, a major accident event, an explosion. So perhaps we view it as a timeline. On the left, in green, the plant is safe. Things begin to go wrong and we travel along that line and the color changes to yellow, to orange, to red. This is where our safety critical elements are failing us, and ultimately we end up at the right-hand side with a disaster. So going back to that idea of the different stages, let's try and identify what's happening. So at the beginning, we hope the plant is running normally. In green, the prevention stage, we're safe. But if those barriers fail, we come through and we have an incident. What do we need to know now? The first thing is that that's actually occurred. It may be that someone sees the flames and hears the explosion. That's not really how we want to find out. We want to have detection systems that warn us very early, very reliably, that the problem's occurred, so we can start to take action and deal with it. And that brings us to the next stage, which is, can we bring it back under control? Can we now turn the corner quickly enough to save the day, to get back to a safe condition? So we need systems in place, we need barriers to try and do that. If that doesn't work, we're moving into mitigation. The event has happened, we're trying to mean that it stays small. We're trying to reduce its effects. But finally, if we fail at that, we are talking about emergency response. So just as a very quick timeline, I'll break each of these down now separately, and we'll look at the safety critical elements we might decide to choose. But for a timeline here, we go from green through to red, through the different stages. So let's walk through one by one and see how that will help us to pick out the safety critical elements that we need. First stage, prevention. We have factors like structural integrity, how strongly we build our plant, or on an offshore installation, the rig, the dock facilities. We look at containment. The first law of process safety is keep the process inside the pipe. Keep the gin in the bottle. And that covers containment, it covers pressure vessels, piping systems, level control. And then, as most of us are handling flammables here, how do we stop them igniting? The difference between a pool of liquid hydrocarbon and a burning pool of liquid hydrocarbon is totally different. So these are hazardous area classification, ventilation, static protection. So these are all things we do, and there are more than these examples to try and prevent incidents happening. Once the accident has occurred, we're looking for detection. This is the first stage that tells us some of our barriers have failed. What can we do? So typically these are detection systems for gas, toxics, corrosion, overflows, alarm systems. This warns us that something now has to happen, and happen quickly. After that, we move to control. So our objective here is to try and regain control of the incident. Try and turn it to being the smallest we can. Keep it in a manageable state. So these may be shutdown systems, blow down, shut off valves, this type of thing. So we're trying to now keep it small and controllable. After that, we're looking at mitigation. These are protective systems, firewater, blast protection, sprinkler systems, breakaway couplings. These are things where we're trying now to keep this in the box. And ultimately, if these fail, we're looking at emergency response. We're fighting the fire. So we have muster areas, we have firefighting equipment, we have extra containment systems, we have breathing supplies, and we have life-saving services. Onshore and offshore, demands are a little different. On an oil rig, you cannot just climb over the fence and run away, so you have to have evacuation capability. But we still have to consider that onshore as well. So as we go through those 5 areas, we can pick out these different categories. And if I summarize them, that gives us a checklist for starting to identify SCEs. So we have typically 8 categories. This is how EGPC addresses it, and that's common pretty much the world over. There are some others that are sometimes identified. And the first 3 here are our prevention systems. The last 5 are our mitigation. So we're wanting to front-end load this. Ideally, we put our effort into prevention so that we don't have to deal with all the mitigation, but we will still have mitigation systems. I just want to pick up one point here before we move on, and that's just a reminder, we're talking here about major accident hazards. These are the very significant but hopefully very rare events, which are often capable of causing multiple fatalities. We also have to manage occupational safety, slips, trips, noise exposure. Those are dealt with by manual handling, by ergonomic design. Those are not safety critical elements because they're not addressing a hazard as serious as a major accident event. It's worth just mentioning that difference because later when we talk about the risk assessment side, we'll come back to this. So we now have a list of categories. How else can we identify SCEs? Well, the other one is safety studies. And under process safety, we carry out hazards, HAZOPs, more detailed studies such as LOPA and QRA. These are approaches which take more resource, more effort, but look in greater detail. So we have the checklist approach from the different categories, which is perhaps simpler to apply, but probably going to be a little conservative. Or we have a more focused approach from safety studies. So those two approaches, if we put them together, give us a pretty robust assessment and give us an opportunity to start making the decision about too much, too little, find the balance. But barrier analysis, the third one here, is where we actually can make that judgment, where we can check how much protection we have, too much or too little. And a very easy way of visualizing that is something called the bow tie diagram, which I'll explain in just a minute. But perhaps let's pick an example and let's start to have a look at something here. Major accident hazards usually have more than one cause. They are, for example, we have a storage tank here, and there are many ways we could lose containment. We could overflow it, the tank could corrode, we might have a passing valve or a failed pump, we may have a vehicle impact. So we have to consider all of those in how we protect. How do we make the judgment of have we done enough or have we done too little? Helps to be able to visualize that. So let's go back to that timeline from green to red. If we separate it, we have prevention before the accident, we have mitigation taking place after the accident. So if we balance that diagram into three parts, before we have the incident and after, we can consider that in terms of barriers from the threats causing it and the consequences as the result. And that's often displayed like this. So in the middle, we have a hazard, which is, in our case, the flammable hydrocarbon. And the top event is that we lose containment. And on the left-hand side in blue, we can consider what might cause that. And then along the timeline, we can put prevention safeguards in. We can put barriers in place. These are going to be some of our SCEs. But also, we want to have mitigation measures after that event has happened. And those we show on the right-hand side, leading to, in red, the consequence, which perhaps in our case is going to be a fire. So as we build these barriers up, we start to see this pattern appearing, which I think probably gives you a hint why they've acquired the name a bow tie diagram. They look like a bow tie. So the next one I want to show you is actually quite a complicated drawing, but I'll explain it, of how we start to fit all these pieces together and how we start to make that decision of where are we strong, where are we weak. So this is an example for a storage tank for a loss of containment. On the left-hand side, we have a number of reasons that might threaten the event. On the right-hand side, we have a number of consequences: fire, explosion, toxic release. And what I've done is I've color-coded the barriers, the SCEs that have been putting in. So in green, these are an engineered safeguard. Those will be my SCEs that I can physically find. Relief valves, shut-off valves, fire protection. In yellow, I have administrative safeguards. These may be inspections, they may be laboratory analyses, things that are carried out by people. And in blue, sometimes you have a combination. So although there's a lot of information on that diagram, the thing I'm really going to look at is to say, where might I be exposed? Where might I be weak? And if I look on the left-hand side, on contamination at the bottom, I only have one barrier. And that barrier is administrative. That is being done by people. And we've already said we know people are not perfect. So that would be one area to focus, to say, do I need other protections here? But on the other side, on the mitigative, I'm looking at, in the middle, the jet fire and pool fire scenarios, where again, I only have one barrier. The green barrier is an engineered safeguard. So if I design it properly and I inspect it, it should be strong. It may weaken, but I monitor it. But the other one, again, is just administrative. So quite quickly, by setting out that drawing, you can begin to look for areas where perhaps you are under-specified in terms of SCEs. And equally, you might look and say, okay, we have 7. Maybe that's too many. So we'll talk about bow ties more again in a future webinar, but they are a very valuable tool to help this analysis, and the EGPC standards recognize that. So the last question then is criticality. We cannot make everything priority 1. We have to use our resources wisely. And the methodology that the EGPC guideline gives for criticality ranking follows what's used by EI and IOGP, which is we create a numerical score. And we do that by looking at 3 components that the SCE has to provide us with. Its capability for dealing with a major accident hazard, the level of consequence that if it fails to operate, and have we redundancy? Do we have backup? And typically, this is the scoring pattern that we use, and I'll explain this on the next slide, so that we can come out with 3 ranks for our SCEs, our high, our medium, and our low, in order to help prioritize not only the resource to manage them, but also the way we design them. So again, just to look at the criticality scoring, the role in a major accident hazard, we want to give high scores to systems that prevent the hazard occurring. The prevention systems are scored much higher than the emergency response. For severity, again, the most severe events we want to give the highest priority to. And also redundancy. If we only have one protection, we want to be very sure we focus on making sure that protection is good. So again, where we have little redundancy, we give a high score. And by multiplying the 3 scores together, we can arrive at a ranking for the SCE. So just to summarize, we've covered a lot of material there quite quickly. We have 2 main ways of identifying SCEs. The first one are the category checklists. And there's guidance in EGPC and EI on individual items that fall within these. And companies often develop their own guidance in addition. We're happy to help with that process. But this is the first quick check, perhaps a little conservative. We can go into more detail with safety studies where we focus more closely. But then to take the two methods, combine them, and look to give the balanced view, we look at barrier analysis, which is where we looked at the bow tie example. So as we move through the design process, we can aim to come out with a package of safety critical elements which focus resource where it's most needed. So again, just to summarize what we've talked about the development of major accident hazard events. We talked about the categories of SCEs that we need as we travel along that timeline. We've looked at the methods for criticality ranking, and we've looked at a way of analysing the loading of our barriers, the bow tie method. Okay. So what I'd like to move on to now is saying, okay, we've identified SCEs, we've designed a series of protections, but how do we set the standard for what they must achieve? What must they deliver? So the performance standard is the document that we use to set out the key properties for the SCE. What must it do? What must it achieve? How do we assure ourselves? How do we check and inspect it so we know it's going to work when we need it? And then what level of verification, of proof, do we need to be certain that on the day that SCE is going to help save us? So this part, I'm going to talk about the first two of these, the key properties and the levels of performance. So for an SCE to achieve its purpose, we've got quite a lot of things to define. The first thing is its functionality. What must it actually do with respect to the MAH event? Next, how available is it? This is the proportion of time that it will be able and ready to perform its function. And for something that's safety critical, we'd expect that to be pretty high. The next one is that on demand, when we need it to work, how confident are we? What likelihood is it that it will work? And this in many ways is the same as what's the failure rate? And again, we would expect this to be pretty high. The other question we then face is we are dealing with damaging events, major accident hazards, fires, explosions. Will our safety critical element survive them? And if it's for mitigation, it has to in order to function after the event. So this is quite an important point we have to look at. And then what interactions, what dependencies do we have? You know, for example, we talked about active and passive systems. Active systems need power. Is that power going to be available if our major accident hazard, our explosion, has wiped out our entire power grid for the plant? So this is where we need to consider, are we talking of an active or a passive protective system? You know, will it survive the incident? Will it be available? And what support does it need? So as you can probably see, these are often abbreviated to the acronym of FARCI or FARCID, covering dependencies. This is a very key point because this is where we define what the SCE must do, and critically, what defines its failure, because that is key when we come to its maintenance. So I'll take each one of these in turn, and I'll pick an example to illustrate it as we go through. But when we're writing these definitions, we may be talking about a quantitative definition, which might be, for a fire water pump, a certain pressure, a certain volume of water within a certain time. Or we may have some more qualitative measures where we're talking about we can start it from 2 locations or auto or manual. So often we have to write both to get a full definition. But if we look at the functionality, we're setting a goal here for what must the SCE do. For example, where must it operate? What's its scope? What is its performance criteria for success? Because importantly, that sets the definition for failure. And failure is what we pick up during maintenance to say, stop. We have a problem because this safety critical element is not working. So what are we going to do about it? And if I pick an example perhaps of emergency lighting, the goal for emergency lighting is to make sure that the control areas, the escape routes, are illuminated during an accident. The scope of it, well, we would achieve that in those key areas by using battery packed up lighting systems, luminaries, in order to give us what criteria? Typically, we would be looking for a certain light intensity, probably 5 lux at ground level. And we'd need that to last for probably 90 minutes. So by setting those, we've now set the failure criteria that says, if our lighting does not provide that level of illumination in those key areas for that period of time, we have to say, we have a problem. Our safety critical element is not meeting its requirements. What are we going to do about it? And that's why the failure criteria are actually very important. If we look again about availability, and I look at the emergency lighting, I want that to be available pretty much all the time, because my plant is, a lot of my equipment is indoors, I don't have natural light. I need emergency lighting to be available at all times. So I've then got to consider, how do I deliver that? Can I trust just by having one emergency light? No, I'm probably going to need several. So in order to make sure I have that availability, because perhaps I need to take some of them out for maintenance, I'm going to have a minimum number in each area. The next consideration I might have is, how reliable are they going to be? The manufacturer tells me that they will always work. Probably not that good in reality. Maybe I get 90%. So I now have another set of criteria that say 90% of these units must work for 90 minutes at the required lighting level when they're called upon to perform. So it's starting to give quite a lot of definition on each of these elements. Survivability. I want those lights to be there and working, but can I buy emergency lights which are fireproof or blast proof? Well, I may have to consider that in terms of where I mount them in the plant. So each of these considerations needs to be outlined. And then finally, what interaction or what are they dependent on? I've tried to address that with the emergency lighting by saying they will be battery backed up. They'll not rely on the plant power supply to work. But again, I then have to remember that's dependent upon those battery packs being in good working order and testing them. So the functional performance specification is quite a detailed document. And that is what forms the basis of the inspection, the testing, and the verification that we'll go on to talk about in the next section. So what are the key points then for a performance standard? They have to clearly define properties and levels of performance. And we have to consider FARSI, functionality, availability, reliability, survivability, and interactions and dependencies. So each one of our SCEs is going to need a performance standard which sets out the basis for our maintenance and testing system. And that's the one I'd like to go on and talk about now. So this is, you might say, the fourth stage. And in my experience, maintenance is always the difficult task. We build plants, we design them. They're brand new, they're beautiful, they work. And then over 10 years, 20 years, maybe even 30 years, we have to maintain them. We have to keep them functioning safely. And that is often, in my view, the hardest task of all. So let's look at what we're talking about for this piece. These are the last two mentioned on that slide. What assurance do we need? What verification do we need? And critically, what do we do when they are impaired, when they don't work? And that is a big chunk. So what do we ask of our maintenance system? It is there to make sure that our safety critical elements meet their performance specification, FARSI, through their life. It's there to gather information to tell us how well this is happening. Typically, we would look to generate key performance indicators, performance measures. And it's there to find and fix the problems, to maximize the availability, to maximize the reliability of these systems. Some big demands. So let's just define what we're talking about for a minute. Assurance, the definition is it's a positive declaration to give you confidence. This is what we're talking about when we're talking about inspection, maintenance, and testing. Because where we have active SCEs, we're testing them on demand. Do they give the result we need? But where we have passive SCEs, we're checking that they've not degraded, they've not aged, our blast wall has not had holes drilled in it for some reason. And where we find problems, we have to do something about them. And hopefully we can repair it quickly, effectively. But if not, we have to start looking at what is the risk assessment we do, what actions do we take, can we carry on running our plant, do we shut it down, what measures have we got? So that's what we're asking from the maintenance system. Verification is when we're wanting absolute proof that these things are being achieved. And within each performance standard, we specify the FARSI requirements. We specify what assurance activities we're going to do to check, to inspect on a monthly frequency or a quarterly frequency. But with verification, we talk about absolute proof. And probably the example where I suspect many of us familiar with here is pressure vessel inspections. Not unusual to have a separate group within the company or even an external agency who do pressure vessel inspections because of the significance of a pressure vessel failing. So that's the difference between assurance and verification. And given that information, what we want to see is a cycle of plan, do, check, improve. We use that information to make sure our maintenance systems become stronger and our maintenance of SCEs remains high enough that they're reliable throughout their life and throughout the life of our plant. And if we find weaknesses, going back to the Swiss cheese model, we find holes in our barriers, we do something about them. We found out why, and we found out how to fix them, and we find out how to make sure they're not going to happen again. So on that question of we find the problems, what are we going to do when they happen? So let's talk about the impairment, whether impairment means failure or impairment means partial performance of an SCE. It is a major problem. SCEs are critical in the safety of our plants, so we have to address this rigorously, robustly. If we can't carry out that repair, how do we make an assessment of what to do? That is described as operational risk assessment. And that really is the main area I want to focus on in this section, because it can be one of the hardest decisions to make and yet one of the most important. So the two questions are, is it safe to continue operating the plant? And what steps must we take, either to shut it down or to continue that operation? So this is a risk assessment. Risk assessments work best with different points of view. Everybody brings some knowledge to the party. But have a bit of consideration for the people perhaps who might have to make this call. That might be at 3 o'clock in the morning with limited resources. So it's important that as part of the SCE process, we provide some guidance as to what do we do if this fails? What steps can we take? Do we immediately shut down? Do we have a prepared plan of what we're going to do? A lot of decisions might have to be made. So the team of people who are doing this, typically we would need input from the operations group. They know how to run the plant. From the process safety team, who understand the major accident hazards and the consequences. From process engineering and technical authorities, specialists in the plant, mechanical engineering disciplines. And what I'm trying to illustrate with the little picture of the three circles there is that when you bring everything together, in the very center, you get one color, you get white, which is all the information. To try and make these decisions without the right people, without the right knowledge, is risky. So it's important that we identify who should be involved, and we give those people support, we give them training, we give them practice, and we give them guidance on making these decisions. Because this is now where the human part of this becomes critical. We have our safety critical elements, we have our pieces of equipment, but here in the middle we have people. And this is where we have to help people to get it right. So here's the mountain they have to climb. At the beginning, our SCE, a safety critical element, fails, and the risk level goes up. But the question is, do we shut the plant down? Or are there things we can do, perhaps turn the rates down, perhaps make additional checks or increase monitoring so that we can bring the risk down to an acceptable level? And how long is that going to take to do? Can we bring it down to a level that is acceptable? And then finally, when are we going to get the SCE return to duty, so everything is back to normal. We have to climb that mountain, we have to find the top of it, and we have to climb down the other side, and we have to do it safely, and we have to do it in a timely manner. So this is where I'm going to come back to my comment about occupational safety risks or process safety risks. This is a decision that, if we get it wrong, can have very severe consequences. We could have a situation of multiple fatalities. We could have a huge fire explosion. So the team needs to focus on that. This isn't a job safety analysis or perhaps a permit for a replacement task. We need to give that team the right information so they understand the significance of this, what could happen, how bad it could be, and any options perhaps for repair. And then, and this is only an example on the next slide, of some of the questions that are going to have to be asked. I'm not going to go through them all now. They're on the slides, they'll be available to you at the end of the webinar. But there are a lot of questions to ask, a lot of decisions to make and say, can we increase the operator rounds checks? Can we find some alternative way of doing this? Or do we have to stop? And it's important that, ultimately, this is not about keeping the plant running. This is about making the safe decision. And again, I'm going to come back to the fact of how do you assimilate all that information? One of the most effective ways of doing that is a bow tie diagram. And what I would particularly direct you to is that the EGPC standards very wisely recognize this. And some standards applied elsewhere in the world are still thinking about this idea. But the use of bow ties is a very effective way of giving that team all the information they need at the time they need it, in a way that hopefully is easy to understand. And again, it links back to our barrier analysis discussions earlier. So again, I've got an example here, which is to talk about, I have a large gasoline storage tank. The high level switch has failed. What do I do? So I'm now at risk of overfilling the tank. My threat of overfilling was protected by manually dipping the tank once a shift. You notice I've colored it orange because it doesn't happen every shift. But I've got level control on the tank. I've got separate level measurement and an alarm to the control room. So that's good, that's green. But this one now, my high level trip has failed. So I've colored it in red. So 3 o'clock in the morning, I am trying to make the decision, what do I do? This way, I can look at all the other things that might cause the problem. I can look at the things which might mitigate the problem if it happens. And I can ask some questions and make some decisions about how do I operate. Do I go and lock the valves off to that tank so I cannot put any more material in it until I've repaired the trip? Do I change the frequency of dipping? Do I have a supervisor verify what's being done? Those are the questions we have to ask. So that's why this is a process that we have to help people to do right. We have to train them to do it right. We have to make it easy for them to get it right. So just to wrap up on that point, what have we talked about? We've talked about the maintenance system, what it must do. We've talked about assurance and verification needs. We've talked about the impairment, the breakdown situation, and the operational risk assessment. And we've talked about methods for making those decisions. All the way through from the beginning, talking about how do we find safety critical elements, all the way through to what do we do if they fail. So with that, let's pause for just a second. Over the last hour, what have we talked about? We've said that safety critical elements are critical layers of protection against major accident hazards. We've talked of the importance of having diverse types, a mixture, a range, different types of SCEs, so that we get robust protection. SCE, MAH events are so bad, we want to be really sure we've done everything we can to protect against them. We set all that down in the performance standards, which sets out what must be achieved, how it must be achieved, and critically, that we follow that without compromise. If an SCE has found to be failed or failed to meet its performance criteria, it is a significant issue. And that's why we need the assurance and we need the verification processes. And that's why, critically, we need the operational risk assessments to make the right decision. Do we shut down? Are there measures we can take? How do we make that decision robustly and safely? So I hope that's been a useful summary. But what I'd like to do is ask somebody who has a great deal of experience in this area to perhaps share some views and some of his thoughts on that one. Amar Hassan, who we're lucky to have with us today as a special guest. And I would value your thoughts and input at this point, Amar. You have seen much of this, I know, before.
Yeah. Thank you, James. It's really very nice presentation, very informative indeed. I want to recap today about a couple of things mainly. The first one is the the difference between design performance standard and operation performance standard, which I will give some example in a bit. And the second topic is the implementation of performance standard, which is very important. Let's get back to the the design performance standard and operation performance standard. I will share with you one of my experience. I was doing a PCM audit for operation facilities, and one of the topics I was discussing with the focal point is the performance standard. So I asked him, do you have performance standard? He told me, yes, of course we have. I told him, do you have it cover both activity, assurance, and verification? He told me, of course. I asked him, can you give me an example, please, or a record? So he go and come back with a design performance standard. I told him, this is for the design phase, not for the operation phase. He said, okay, but this is what we have. So having a design performance standard is great, but it will not help you much during operation stage, in particular, when you have an aging facility after 20 years. So the difference between both of them is the following. The same, both of them, they follow the same approach. It's the same methodology, which is James mentioned, which is the FARSI. However, for the design, the assurance requirement is focused only on the design specification only. It has nothing to do with the operation. For the verification activity, it is normally happened during the design phase. It happened with a subject matter expert in the area. So, for example, if we do performance standard for the shutdown valve, should be combined between process team and process safety team, and it normally happened with independent consultant, which what we called ICP, independent competent person. So it is happening with the subject matter expert, independent, and have a lot of experience. This is during the design phase. If we go to the operation performance standard, it has completely different expectation. the assurance activity is mainly for the preventive maintenance. So if you see the difference, so if you see the design performance standard and operation, it looks the same as the topics, but the content is completely different.
Yeah.
So for operations, we have to make sure the proper preventive, which is the assurance activity, the proper preventive maintenance are set in place. And if we go to the verification requirement, is also completely different from the design phase. We said for the design that he has to be a subject matter expert. For the operation phase, it's not necessarily. Why? Because the nature of verification during the operation phase is the witness test review record. Does not need a subject matter expert, but does need an independence. So I cannot have the maintenance team. He bring his colleague to be a verifier. No, should be from other discipline, from the company. It doesn't have to be a consultant within the company, but from different discipline. So I just want to highlight this. It's very important. It's nice to have a design performance standard. It's great, but during operation phase for aging facilities, the operation performance standard is a must, and this is one. It will help you to maintain the safety of your plant. This is the first thing. The second topic I want to recap and touch is the objective of the performance standard. The ultimate objective of the performance standard is not to develop a very good performance standard, is to implement the performance standard.
Absolutely.
In order to be implemented, it has to be achievable. If I do something extremely high expectation, sometimes I will not be able to achieve to fully implement the requirement of performance standard. Okay, as James said, we have two topics: the assurance requirement and verification requirement. In order to make the assurance requirement achievable, is what James mentioned is the criticality ranking. It's very important the team who puts the input for the criticality ranking is competent in order to have something, a sort of level of categorization. I can utilize the maximum use of maintenance team for the maintenance of the performance standard. So this is for the assurance activity. For the verification activity, when the consultant who is supporting you to develop the performance standard share with you the nature of verification and the frequency, you have to review it very thoroughly and make sure that this is meet the resources within the company. Because if I put too many verification activity and you have very limited resources, simply you will not be able to comply with this expectation. So I encourage you to review the frequency of verification activity very well before have the final performance standard, in order to be able to achieve the requirement of verification activity. By doing these two areas, the proper criticality ranking and fit for purpose verification frequency, I believe you will be able to implement the performance standard, which is the most important target. The target is not to develop performance standard. The target is to implement the performance standard.
Yes.
So this the couple of points I want to share with the team and with James. Thank you very much, and I'll get back to James. Thank you, James.
Thank you, Amar. I mean, yes, I absolutely agree with your points there. The difference between the design performance standard and your operational performance standard, bearing in mind your operational performance standard will live with you for 10, 20, maybe 30 years. That is the one that really matters. And as you say, having a perfect performance standard that you cannot achieve, it's not going to help solve your problem. You know, that important point of assurance and verification and proof, because safety critical elements are, you know, by definition, as you said, they're critical. But yeah, really thank you for those points, and I would totally agree with them. It's so important that it's using the performance standard is what matters. And, you know, again, we've talked about that plan, do, check, improve process. Things will evolve. The plant will change over its life. You have management of change. You have all those systems in place to help monitor what's happening, so that it stays safe all the way through. So yeah, thank you very much for that, Amma. Wise counsel. Thank you.
Thank you, James.
Okay, so with that, I will just hand to Naomi. I've not actually looked at the chat and seen if we've had anything come in on the questions. I think you said there were a few questions. I'm not sure how we are on time. I'll let you run that.
No problem. So thank you for your presentation. And here are some of the questions that came up. And just as a reminder to any of the attendees, if you haven't already done so, we're going to ask that you type any more questions into the Q&A box in your control panel. So first question, James, how many SCEs would you expect to have on a typical petrochem plant? And what percentage of items on the asset list would be classified as safety critical elements?
I would, in my experience, I would be looking for something where you are probably talking between 10 and about 20% of the tag items having a safety critical function. It varies. It depends upon the process. It depends on how many major accident hazard scenarios you have for a plant. But it often seems to come out as a reflection of the 80-20 rule. You know, 20% of your rather more 80% of your safety benefit is coming from 20% of your equipment. I have heard of cases where it's been as high as 40 or even 45%. And in review, those operators have said they have found it incredibly difficult to actually manage and run their systems because the testing, the maintenance demands are so high. And as Amma said, you know, the point about prioritization comes into play. It's not possible to have everything at priority one. We have to make some judgments. We have to gather data to prove that. So I would say somewhere around the 20% mark. And from talking to my colleagues, I think that's what they've seen as well.
Great. Thank you for that. Next question. Can you explain a little more about the difference between safety critical elements and safety critical equipment?
Yeah, that can be a bit of a tricky one because unfortunately they sound very similar. And I often use the comparison of leaves on a tree. The safety critical element might be the tree, but the safety critical equipment might well be the leaves on the tree. There is a decision that you have to make when you get into more detailed analysis. Perhaps let's talk about a gas detection system as an example. Not every single component in that system is going to be truly critical. They may be beneficial to the function of the system, but not every single perhaps junction box or sounding unit might be critical. It's the overall performance of the system we're looking at. So I would often say the difference between safety critical elements, they're the tree. Safety critical equipment are the leaves on the tree. And you can afford to lose a few leaves off the tree and it will still survive. You lose all the leaves, it will die. So I would use that picture if that helps clarify it a little.
Perfect. Next question. I think you mentioned 8 categories of safety critical equipment. Are there any others?
Those are the common ones. Some companies like to have some slightly more specialized ones. For example, I mean, rotating equipment is something that sometimes crops up, where you may have generator systems or certain compressor systems which are critical. But those are the common ones. I mean, they get picked up in eGPC, in IOGP systems. They're the main ones. But sometimes it makes sense for a certain operation to have a few other categories. But I would counsel against creating a lot. The benefit is those really are serving as a checklist, and checklists are very good for known situations. So really creating more categories probably isn't helping you hugely. They give you a good way of checking down a list, starting to identify the number of safety critical elements, but probably in a slightly conservative way. And that's always a good thing at the beginning of a process. But I would say, yeah, maybe if it fits for the operation, add a couple, but perhaps 10 should probably be enough.
Great. You showed examples of bow tie diagrams. Is there any standard or guidance for the number or type of barriers there should be along each line?
There is no, as I might say, statutory or regulatory guidance that I'm aware of. I know certain operators within oil and gas have a requirement for, I think it's a minimum of 3 barriers to be present. And I think the policies tend to be only that at least 2 of them should be engineered protections. So in the example that I showed where we talked about only having 1 administrative barrier on one side and 1 administrative barrier on the other, that would not be considered acceptable. But it really is down to the severity of what you're dealing with. And there are ways in bow ties of doing more quantitative, typically like a LOPA study, a layer of protection, where we put reliabilities in. But that can be quite complex. And I think generally I'd say 3 is a good number, but always remember to give some consideration to how strong you think those barriers are going to be. Remember that humans are not perfect. And remember that your engineered barriers have to be maintained in order to be good. So as a long answer, coming around to saying probably 3 is a good number, but that's not a hard and fast rule.
All right. And then the performance standard has many parts. Which would you say is the most important?
I would entirely support Emma's view that this is not about producing a perfect performance standard. From my own approach, and this is coming from quite a long time in the operating side of running chemical plants, I personally feel the most valuable bit is the failure criteria, because that's the decision that says we have a problem, we have to change what we're doing. And the change might mean we have to shut down. The change might be we have to derate our operations. The change might be we have to bring in additional checks or fit other equipment. You know, the management of change triggers that need to be considered. Because if you don't define what failure means, it's dangerous, because someone may say, well, we haven't really failed, we're okay to continue. And we need to be very sure that that's the right decision to make. So I would always say, make sure you give good consideration to the consequences of failure, and therefore make sure that you define it very well.
Great. And it looks like we've run out of the time for the webinar, so I'm going to ask one more question
Okay,
before we
yep.
conclude the presentation, and
I'll
then
try and be quick.
your closing remarks. But the operational risk assessment seems to be something which will be difficult to carry out. Can you explain more about it?
It can be difficult if you don't have the right information, you don't have the right people and the right skills present, and you've not had training and coaching in how to do that. Carrying out risk assessments is something that happens a lot at the design stage. We do HAZOPs, we do all these studies. But I would always say, please think about the people who in 15 years' time are going to be running the plant at 3 o'clock in the morning when they're suddenly told this piece of equipment doesn't work anymore. And if they've never been trained, if they've never been coached through that type of decision-making process, which it is different to the decisions you make when you're writing a permit or you're investigating a minor incident. It's possible to forget that what you're dealing with is something which is there to prevent perhaps a major explosion, perhaps a major fire, perhaps the deaths of 10 or more people. That's a bit of a frightening concept if you've never had to face it before. So I would always say it's important as part of this process to think about who will be doing that in 15 years' time when everything else is filed away and forgotten. I've been there myself. I know what it feels like.
Oh, man. Great. Well, it looks like we've only covered just a few of the questions that were asked. And to our attendees, again, if you have any additional questions, I'm going to ask that you type those into the Q&A box, and we'll have James answer those. And after, we're going to actually host this one more time. We know a few people were having issues logging in, so we are going to do another presentation for everyone. So we'll combine all the Q&A, questions, and then have you guys answer those, and then we'll send out that recording via email or newsletter, and we'll also post it on our LinkedIn, which will have links to the recorded webinar, slides from this presentation, and then the recorded answered questions. So thank you so much, James, and everyone who attended.
If I can just add, I would say thank you to everybody who's attended. Thank you to everybody who's raised questions in the chat. I'm sorry we haven't been able to address them all today, but as Naomi says, we will send out this information and we'll cover all of those. I thank you very much for your time and your involvement in this. I'd like to thank Amar as well for his guidance and wisdom on this as always, and to invite you to the next webinar in this series, which I think is probably scheduled for around July.
That's correct.
And there will be more to follow. So again, please, in the questions or in the surveys, if you have thoughts and points of interest, either to expand on what we've talked about today or for other topics, please let us know. We're here to help. We're here to provide this help and guidance. So please, your ideas, thoughts are very, very welcome. And I would say have a safe day, take care, and if you're traveling, all best wishes for the journey.
Thank you, James. Bye-bye, everyone.